We turn to discuss image priors. As we are about to see, an evolution of ideas on how to build P of X defines much of the image processing literature. Here is a central fact that experts in image processing never speak about. Much of the work done in our field is centered on the choice of P of X. Indeed, many of the papers published over the past several decades are nothing but an evolution of ideas on how to choose P of X and then how to use it to handle actual tasks. You might think that the above statements are unique to image processing, but actually the same is true for many other subfields in signal processing. Priors are everywhere. So how could we identify P of X for images? Think about it. This does look like an impossible task. Well, rather than daring to ask about P of X directly, let's identify properties that natural images tend to obey. This brings us to the very naive, and yet very important, spatial smoothness idea that emerged in the 60s and 70s and actually never left the building. We could evaluate how smooth an image is by measuring the L2 energy of the outcome of the Laplacian operator applied on our image. This suggests a PDF of this Gaussian form, which leads to a high value for very smooth images. Suppose that we believe in this prior and we aim to address inverse problems armed with it. Recall our earlier map suggestion. The restored image is the one maximizing the probability while being inside the measurements ellipsoid. This can be rephrased as the minimization of the Laplacian L2 energy. Turning the constraint into a penalty leads to a somewhat more pleasant problem and to this optimal solution. This is the well-known Wiener filter. The benefit of this L2 based prior is clear, as we got a closed form solution. So should we be happy about this result? Definitely not. It is well known in image processing that the Wiener filter is poorly performing and its results are unsatisfactory to say the least. So what shall we do? Well, don't be alarmed, as this is only the first step in the evolution of image priors and better ideas are about to come. Before moving to truly better ideas, we should mention other closely related branches of thoughts. For example, some researchers truly believed that the path to a reasonable choice of P of X passes through well-known transforms. If T is a forward transform of some sort and lambda is a diagonal matrix, this expression offers an alternative prior. Its rationale is to force some transform coefficients to be small while untouching the others. In fact, one could argue that this is the prior practiced by the JPEG compression algorithm. Interestingly, both these priors are Gaussian, as both rely on the L2 norm. Indeed, we could even make the two identical by forcing this relation between the Laplacian, the transform, and the weight matrix. Now, here is something a bit confusing. We all know that JPEG performs rather well, but just a minute ago I told you how poor the L2 priors are in the context of the Wiener filter. So how can we resolve this conflict? We'll come back to this question later on. Could it be that the flaw in the above two priors is the arbitrary choice of the Laplacian or the transform used? How about learning the distribution from image examples while keeping the Gaussian structure? This is exactly the path of thinking that led to the Karonin-Loeb transform, KLT, also known as PCA, Principal Component Analysis, and this is how it looks. The matrix R is learned from image examples, and thus this approach is expected to be better, right? Well, as it so happens, at least when it comes to small image patches, this approach aligns nearly perfectly with the transform case in which the 2D discrete cosine transform is used. So no, this is not really such a great idea after all. What is it that undermines the Wiener filter? What is truly wrong with the priors that we have just presented? Visually speaking, restoration results using these priors tend to be over-smoothed. This became gradually clear during the 80s, along with the identification of the villain in our story, the L2 norm. Squaring the Laplacian value on edge pixels leads to a huge penalty, explaining the over-smoothness. The remedy suggested at first was weighting. So, rather than penalizing all pixels equally, those suspected of being edges get some sort of a discount. W is a diagonal matrix that reduces the penalty for pixels suspected to be edges. You may wonder, how come we know W? And yes, you will be right. This is a shortcoming in this approach. Observe that with this modification, we are still in the Gaussian regime, but this is about to change. In the late 80s and during the 90s, the above rationale matured into a clear departure from the L2-based priors. No more Gaussians. The alternative came in various forms, emerging from robust statistics, borrowing ideas from partial differential equations, and yes, sparsity came into our lives. Here is the robust statistics prior, which better handles outliers such as edge pixels. Here is the total variation penalty that is tightly related to partial differential equations. This penalty simply accumulates the absolute gradients all over the image. And here is the first sight of sparsity, suggesting that wavelet coefficient should be few. Common to all these options is the idea that the image distribution should be heavy-tailed. Observe how all rely on the L1 norm. Interestingly, using these priors in restoration tasks lead necessarily to nonlinear filtering. However, we should not be afraid of this trend. In fact, it is fascinating that these priors give us a systematic way to design nonlinear algorithms with a clear objective. And now we jump forward to the more recent and more effective priors that emerged in the past decade. The field of experts generalizes the robust statistics option by using several robust terms and learning the filters LK and the influence functions rhos. Sparse modeling in a much wider context became central, accompanied by learned dictionaries. There are other options, such as Gaussian mixture models, low rank assumption, and more. Common to all of them is the fact that they are adapted to the data by learning. Also, sparsity is key in each of them, even if not seen explicitly. I have just given you a glimpse into the evolution of image priors over a period of 4 decades. The main themes in the better behaving methods are the migration from L2 to sparsity promoting measures such as L1 and even L0, and adaptation to the data source by learning. Have you noticed that all the priors we mentioned admit a Gibbs distribution form in which p of x is an exponential of some negative energy function g of x? So our quest was really about g. Naturally, in choosing the Gibbs form, we lose no generality, as any PDF can be described this way. The benefit is clear, since oftentimes we will apply a logarithm on the prior as part of our derivations, and then we simply end up with g of x.